Imagine a function f, and imagine finding the equation of a line tangent to f at some x value. I'll call that x value a. So here's a picture of what I might have. I have a function f that's drawn in blue, and I've chosen an x value called a. And at the point a comma f of a, I've drawn in red the line tangent to f. So near the place where x equals a, so near a comma f of a, that tangent line like really hugs the graph. It's a really close approximation of the function, as long as I promise to only look really close to where x equals a. That's what we did in those first couple of days of school, where we zoomed in on a function and watched it flatten out. If you zoom in on a function so much that it appears to flatten out into a line, that line is the line tangent to your original function. Or that line would have the same equation as the line that's tangent to your function. So this is a technique we can use. Derivatives help us out because to find the equation of a tangent line, we're going to need a slope. If we ever need to approximate a function, imagine you're using a computer and it takes a lot of computational power to multiply or divide or evaluate your function. But imagine you could write a function that's linear, that's a really good approximation of your function. It saves a lot of computing costs, and we can use that to make approximations of the function without doing really expensive computations. So 4.5 is all about using the tangent line to a function at a particular x value as an approximation function for that original function near that same x value. And when we do that, the function that we write, the tangent line that we write, is called the linearization of the original function. It's like taking that equation, the original function, and turning it into the line, the one line that's like the best line. If you had to use a line to approximate that function, the best line to use is the tangent line. So you can watch these next couple of slides. Really, I'm just going to take point slope form for the equation of a line and rewrite it so that the y is isolated. That's going to give us a function that's linear, that's the same function that we would get if we use point slope form to write the equation of a line. So y minus y1 is m times x minus x1. The x value I care about, in the last slide I called it a, so that's what I'm going to do here. The x value that I care about, I'm going to call it a. So what's the y coordinate that goes with x equals a? Well, I'm going to use a as the input to my function, which is named f, so my y is going to be f of a. What am I going to use for slope? Well, I know now for slope I can use derivatives. So if I want the equation of a line tangent, I'm going to use the derivative. Notice this is I called it out in the notes in the top of your 4.5 handout. It's not just enough to find f prime of x. I need a slope that's a number, which means I'm going to evaluate that slope. I'm going to evaluate that derivative at a. So I'm going to call that f prime of a. Notice this is not f prime of x. F prime of x is not enough. I need to find f prime of x and then evaluate it at a. So this is just point slope form with all of that stuff used in the right spots. And in order to write that so it looks like a function, I need the y by itself. So that's why this minus f of a got added to both sides, and I see it over here as positive f of a. So this here in the yellow box, that's a formula for the linearization of f at a. It's really just point slope form for the equation of a line with everything moved over to one side except the y. So if you want to memorize that formula, some students like to do that. If you want to just say, oh, I already know point slope form, I'm just going to make sure at the end I isolate the y, that's fine too. And then once you have a linearization of a function f at a particular x value, then if you need to know the y value of your original function at some x that's near the x you know, we can use this linearization to approximate it. So f of x is going to be approximately equal to L of x as long as the x value that I use is near a. All right, that slide kind of summarizes things I just said. That function, once I've isolated the y in the tangent line equation, what I have on the right-hand side is a function of x, and I can write that as L of x. That's going to be a function that tells me output values, approximations for output values to the original function, as long as my input value is near the original a. I'm just going to point out that you may have spent some time in your Algebra 1 or Algebra 2 class taking that equation and distributing and like changing it into slope-intercept form. Just notice that I promised the math that we're going to use this function for. It's going to be much easier if you don't distribute. So that's just a word to the wise. You're going to get the same answer either way, but I promise the math is going to be easier if you don't distribute. Okay, and then, again, that's just point slope form with y isolated. So how can I use that? We're going to practice here. This isn't a very calculus-y example, but just kind of get us started. Imagine cosine of x. And I need to use a calculator to find that. But this linearization technique is going to give me a way to give an approximate value for cosine of 1.75. So here I go. I'm going to need the linearization of my f function. That says f of x equals cosine x. This should be the word at here, the at printed in a funny place. All right. So to find the linearization, I know my a is the x value I care about, so my a is pi over 2. I'm going to need, I have f of x is negative sine of x, and I'm going to need to evaluate the derivative, so find the slope of f at that x value, which was pi over 2. So f prime of a is f prime of pi over 2, which is negative sine of pi over 2, which is negative 1. So now I'm going to put it all